Okay, let me start with the discussion about one paper, and thank you for the invitation. I will talk about data-driven robust optimization unit commitment. So this is actually joint work with my colleagues Alexandre Velloso and Alessandro Strip from Rio de Janeiro. My colleagues Jose Manuel Arroyo and Noemi Cobos from University of Castilla-La Mancha. Basically, most of this work have been actually done with them, and I just here just to present this work. So the presentation is based on this paper, which was published last year in IEEE Transaction on Sustainable Energy. So this is the long title of this paper. Okay, and let me start with the motivation. I feel like it's clear the motivation, like now renewable energies actually form, it's a big share of the new capacity which is added. And actually it's kind of challenging operating power system with these new renewable energies. They basically, because they are not dispatchable, and they have very complicated patterns in terms of behavior. So it's very complicated actually to give some specific models for incorporating this renewable energy generation variability into power systems. We can see here like a very classical example from one wind farm in California, which you can see like from one day to another day, actually it's a chaos. You cannot follow a pattern from one day to the next day. And in average, things are not working properly. So I think like we need to, in somehow, to consider not only just the average values or some specific. So this is actually called a spaghetti chart because it looks like that kind of a spaghetti dish. So the challenges of renewable energy integration in power systems, specifically in the operation, which is the thing that we are going to deal here today, it's related with it's actually a multi-dimensional problem, the renewable energy modeling or just representation, because we have around, well, system actually can have tens or thousands of uncertainty elements, like let's say from tens wind farms up to hundreds or thousands. There is also some uncertainty related with the temporal component, like from 1 hour to the next hour, actually we are expecting to have some correlations, and there is some important feature that we can actually make up sure. And there are not only renewable energy generation, like the uncertainty element that we can find in the operation of power system, but also we can find other elements like demand or even availability of the elements, sometimes called N-1 or security criteria. Correlation exists in this multi-dimensional, so we cannot think like each of these node or bus in the grid can be understood like independent from others. Actually, there is correlation between them, and we in somehow we like to acknowledge and to capture this in the best way that we can. So this actually is very complicated to try to forecast, because they have nonlinear behavior. There is time variant dynamics, and there have been a lot of works done in these directions. And here we are proposing, I am showing some of our ideas of how to deal with this type of uncertainty. You see here on the left, this is well, on the left, also on the right. So you see this is a wind forecast. This is the wind patterns for I think it's 30 days, if I'm not wrong. In one dimension, you have the hour of the day from 1 to 24, and this is in here in these two other dimensions, we have the normalized wind power output, normalized from 0 to 1. Okay. And in red and blue, you can see like 2 particular days, how was the evolution of that. And that you can see like in somehow they could find some correlation. It's very complicated to give a specific model, like a multivariate Gaussian distribution. And then, well, the fact that we have data actually is a very good thing, like because we want to somehow to use this data to incorporate into the decision-making models, in particular, in this particular case, in the operation, in the unit commitment problem. Okay, so more observation about this data. Typically, this is again, this is from this data is, was taken from this global energy competition, and this was based on real data. I'm representing here, for example, in the x-axis, what was the output of a particular renewable energy generator, like in a particular node, from 12 p.m. and here at 1 p.m. So of course you can see like every dot is representing one day. Like let's say we can say like previous 30 days or 40 days. And every dot is representing one day. And then you can see like from now 1 hour to the next hour, we can somehow observe some particular correlation, right? And the idea here is like, well, I don't want to actually to fit this data to any particular model. I don't want to start to make assumptions of what is the distribution that is following this data, etc. So I want just to take this data in somehow and to consider any possible outcome in the future just based on this data. We also observe like from our 12 and then 6 p.m. So 6 hours later, practically there is no correlation. You see like the variability goes from 0 to 1 and here goes from 0 to 1. This is per unit. It's normalized wind output, wind generation output. So the overall idea of this paper was just to create some sets or complex set that is representing any possible output. For example, in here, any possible output will be within this set. And we just decided to just take data as an input, and any value which is within this convex hull represented with this data will be a possible output. So this is one of our main assumptions, that this renewable generation will be within this type of uncertainty set. I will come back later again. We also observe a spatial correlation, and then if we look, for example, this is one particular hour in bus 5 and bus 6, which are closed in a particular grid. So you can see like there is also some kind of positive correlation. Okay, this is good because I would like to capture this fact. So for instance, if I'm building this type of uncertainty set of this domain where my possible output can be living, so I can see like I can say like, for example, if wind in hour 12 was high, so I'm expecting to have high wind in the next hour, or anything within this this set. In the other way, if I have low wind output in hour 12, I can have any output within these these values, but I cannot have like for zero output or very low output of wind production in hour 12. I cannot have high wind. Okay. So this is the idea, and somehow this is actually capturing correlation. These uncertainty sets, or these sets which are based on the data points, actually can capture the correlation. So we would like actually to extend this for any dimension. Okay, this is the kind of the key idea. We can observe also another variations on wind patterns that are not only dependent on the particular position in the grid or the bus and time, but also along the time. For example, in Latin America, they have some climate phenomenon they call La Niña, El Niño, which actually representing some dry seasons and or dry years, and then they have also some wet years. But actually, it's changing quite a lot, the wind patterns. In some particular places, the wind patterns I'm showing here, like in orange, you see here some particular output. This is average wind, of course, for 2 years, where we're classified like El Nino. And then you have other patterns here in blue, were classified La Nina. So you can see like even the wind output in average can actually change along the years in some particular places. In this case, can go even up to 20 or 30%, even 40%, even probably more. Okay, this type of uncertainty, medium-term or long-term uncertainty related with these climate phenomena are not considered in this problem. So we are looking at the problem of the day ahead dispatch based on unique commitment. So what is the motivation of this talk? This is just to formulate and to solve the classical unique commitment problem with the minimal parametric information. And parametric information means like I want to give the minimum assumptions on the type of on the way that I'm modeling the stochasticity of my uncertainty parameters. And of course, so renewable energy generation is a key component of this unique commitment problem. So what is the framework that we are selecting here is data-driven robust optimization with the methodology that we are going to employ for solving this problem is called column and constraint generation. I will explain in detail each of these particular case. Okay, let me jump now to the mathematical formulation. So how I'm dealing with this type of with this particular problem. Let me recall what are the most classical frameworks for decision making under uncertainty, and in particular in two-stage decision making under uncertainty. So in two-stage decision making under uncertainty, we have one stage which have to where we have to give some decisions. In this case, are represented by X, and this is also called here and now. So those are decisions that I have to make right now. Then I have a second stage that I have to make kind of I have some recourse actions after I observing some random realization, some uncertainty which is realized. Okay, so the second stage also is called wait and see. In particular, the decisions. Sorry. Yeah, decisions are called wait and see decisions because we have information of the uncertainty already, so it's not uncertain anymore, and we can make the decisions on our specific scenario, right? So in well, some kind of representation is like this. I have to decide X. Now this is the first stage. And then in the future, I may have a different possible realization. For every possible realization, here they are represented by KC. So this is the case. KC1, KC2. I can actually have some recourse decisions, which are represented here by Y. Okay, and this is the typical framework for two-stage stochastic optimization. The important thing here is like we have to make an assumption that we have perfect information about the true distribution of the stochastic process. Let's say like this case is representing the uncertainty output of one wind farm. So we need to have some information about what is the distribution. It could be empirical distribution, or it could be some other analytical distribution. But the expectation here actually is over P. P is a particular probability distribution function, and this P is known. So it means like I need to give, I have probabilistic information of every possible scenario. Okay. So this is not probabilistic and agnostic case. Actually, you need to have some information of possible scenario. So I'm representing here a finite number of scenarios, and this is could be the case that we have empirical distributions. But if we have continuous distribution, the typical thing that is done is just to sample, right? The sample average approximation. Okay, there is another approach for dealing with this type of problem, which is called two-stage stochastic optimization. It's also called adaptive and robust optimization because we have the possibility of adaptations in the second stage, which is have the same structure of the two-stage stochastic optimization. We have some decisions to make in the first stage, and then there is another type of decisions or the recourse or this adaptation in the second stage. The difference here is like, well, we are now considering the minimal information that we can have with regard to this stochastic parameter Cousin. And this minimal information can be just the support. Where is the bounds of the values that it can take my uncertain parameter. For example, for the case of wind production in per unit, it could go from 0 to 100. It can produce 0. It could be a full capacity, right? This could be the particular bound. Of course, this is one dimension, so we can think this could be extended to 2 dimensions, 3 dimensions, of n dimensions. The particular feature of this robust optimization, of this adaptive optimization, is we are going to decide, we are going to make a decision in the first stage in such a way that my recourse function will be optimized for the worst case scenario. So I'm looking amongst all the possible scenarios, I'm looking for the worst case scenario. And this worst case scenario actually depends on endogenously on this first stage decision. Okay. So but then there have been a lot of work done in this direction. And in principle, you can say that this is a bit more conservative than the previous case, but you don't need to have assumptions on the particular distribution. And so it means like we don't need to make any assumption on the probability of one scenario will happen in the future, okay? There is also some directions on dealing with this type of two-stage decision problems or this optimization necessity, which is called distributionary robust optimization, okay? And distributionary robust optimization can be understood in something in between two-stage stochastic optimization and adaptive robust optimization. In distributionary robust optimization, now we assume that my uncertainty it's actually represented by a family of probability distributions. Okay, this family can be discrete number of distribution, or it could be an infinite number of distributions. This family actually is known like an ambiguity set. Okay. The structure of this problem is just, well, we minimize this first state decision variables. In the particular case of the unit commitment typically are the generation, dispatch, the startup and shutdown constraints, and reserve in the case that we are optimizing energy and reserves. Then we have, again, we have a second stage. We will adapt to the observations. But in this case, we assume that we don't know this probability P, and then probability P is lying in this particular family of distribution, which is represented here by calligraphic P. And the idea of making this robust is just, well, I don't know which distribution will happen in the future. So let's take the worst case distribution. So the second stage of this second part actually is representing the worst case expected cost. Okay. Well, for this distribution and robust optimization, again, we don't need to give a particular probability for every scenario, we know families of distribution. So this in somehow is a probability agnostic case. And there have been quite a lot of work done from simple, let's say, simple ways of representing this family of probability distribution from Chu and Fukushima, where you have a discrete number of distributions, and then you find what is the convex combination of these, in this case, particular case, 3 distributions. We can have information about moments, like first moment, second moment. It can be like a perfect information about this moment. So I know like what is the particular mean value, or I have some ambiguous information of this mean value. Okay. Yes, so you have works from Bertsimas, this Dilek and yeah. And there is also the possibility of writing this ambiguity set based on a statistical distance from two distributions. So I have, let's say, this this distribution in gray, and this is kind of empirical distribution with some observation, and then I can actually find what is the worst distribution. So this is representing families of probability distributions. Okay, but in today's talk, I can discuss this in a different moment. We have also some works with the same college from Catholic University of Rio de Janeiro in distribution and robust optimization. But today I'm here just to discuss about robust optimization itself, this framework. How has it been used in the context of power systems? So the first work, one of the first work in robust optimization in the context of operational research community was the paper of Soyster. So this is kind of very classical model that let's assume that we have two uncertainty or two stochastic parameters which are uncertain. And I have also information about the, let's say, it could be some reference value or nominal value. It could be, for example, empirical average. And I can just say, well, from this empirical value, like this average, like could be like point forecast of the wind production in node number 1 and node number 2. Okay, this is a kind of the forecast. Around that, so I can build some uncertainty set, which is called some set which try to capture any possible output of wind production in 1 and 2 that we think this is possible. So we are adding some deltas, so some incremental incremental on the positive side, also in the negative side. So basically, we can say like the Ci plus, yeah, could be from some delta C minus some delta. This is 1, this is plus, and then, well, we have some particular variables that they are modulating how much we are taking. So any value within this gray area will be possible. So my two-stage robust optimization framework actually can respond to any possible output which is within this gray area. Okay, but you can see like this is kind of a very conservative case. Then Benthal and Nevirovsky in 1999 actually come up with the idea of, well, instead of building these Bosc uncertainty sets, let's do something which can be transformed from multivariate Gaussian distribution to some other uncertainty set. So multivariate Gaussian distribution, when we have this correlation, can be actually very well represented with these ellipsoidals uncertainty set. So this is the case that Benthal and Nevirovsky actually wrote. In this particular case, we can have already a correlation capture. So for this uncertainty set, we see like there is a positive correlation. It's not possible to have high, low win and high win or low win and high win. So this is outside of this uncertainty set. So those scenarios are not possible within this uncertainty set. Then actually the problem of that is you have ellipsoids, and then there is you have second order quadratic constraints. And in 2004, Bert Simas and Sim actually published a very popular paper. I think the name was The Price of Robustness, if I'm not wrong. And they actually extended the work of Soyster to any possible polyhedron, or polyhedron. So we can say that we have some uncertainty set will be represented by linear set of equations. And this is extended for any type of site. And these actually have nice interpretations. For instance, in the case of Soyster approach, it was this gray box. And by adding additional constraints to this Soyster, we can reduce the conservativeness. For example, I can say like, well, neither KC1 and KC2 can only vary only once at each time. So I can have the maximum value or the minimum value of one of them, but not two of them at the same time, simultaneously. So this is basically one of these constraints. This is basically one of these constraints. This is one of these constraints, and this is one of these constraints. And this actually is represented by this, what is called budget of uncertainty. So this was a very nice interpretation. Like, as I'm increasing these values of uncertainty, I can actually allow to have more elements that can vary to the extreme values. If I want to decrease, I can say I will not have everyone in the worst case possible output, like all the wins. Like, so one wind farm is at the very top, and the other one is the very bottom. So I'm not going to have that. So this actually is giving you a nice interpretation, but it's very complicated to decide what is a proper budget of uncertainty. And I will show you in some examples. It's very, very complicated. And this is something that the user have to define. It's a parameter defined by the user, how much budget of uncertainty I want to have. Okay, this is nice. And somehow it can capture a correlation, but it's not really clear how you can capture unless you have some fancy way for describing this uncertainty set. And then the last work, and this is the work that we have actually implemented, the way that we design the uncertainty set is just based on data. So we have some observations of historical data. And these observations are like the previous one that I show. Like, we can actually see all those values. And then I can say, well, let's assume that any possible, this is two, any possible output of wind farm 1 and wind farm 2 will be within this convex set. Okay, and then by definition, I'm just defining the convex hull of all these possible the observation as my uncertainty set. Of course, one can think about even adding some slack, like, well, we can increase this boundary with some slack values that we can design. But this is something that we probably will explore in future, but we just define like uncertainty set as the convex hull represented with all these dots. So we assume, like, for tomorrow, for the day ahead, any possible scenario which is within this data-driven uncertainty set will be actually feasible for my optimal unit commitment. Okay. So most of the works that have been done in robust unit commitment was based on this budget constraint uncertainty set. Okay, it was based on this Bertsimas and Sim paper from 2004. There is a lot of variants of this budget base or budget constraint case. And then here there are a few papers, but I think like there are probably more papers that I probably am missing. Some from Lorca and San, Moreira, Zheng, Dai, Wang, Xiao, and there is also a very interesting paper from like a discussion paper on this robust optimization problem and this uncertainty set construction. So what is the compact definition of my robust unit commitment that I'm dealing with in here? So this is very compact. I want to give, I will give you some details. So I want to minimize some efficient X, and this function is representing the operational cost, which actually accounts for energy dispatch, startup cost, fixed cost of the online units, and reserves, which is yes in there. X, of course, have to be in some domain. This problem itself is the classical deterministic unit commitment problem with all the details that you want to give. Okay, and this is typically a mill problem with these binary variables representing online units startup and shutdown units and ramping constraints, etc. Typically, this set X actually is within some nominal values of renewable energy generation. It could be like point forecast or average value, whatever, but it's usually some reference value, which is the practical implementation in most of the power market that they are using unit commitment for day-ahead dispatch. Well, we add on top of that an additional constraint, which is some limitation of worst case imbalance. This phi is representing the worst case imbalance. And it's a function, okay? It's a function of the worst case imbalance. And imbalance means like load shedding, wind spillage or renewable curtailments. Right. How we can actually compute for any possible scenario which is living with some uncertainty set, we will try to find what is the worst case. So I want to find what is the worst case imbalance. And this worst case imbalance is given by this U. And this U is representing this uncertainty set. We will run this data-driven option that we are presenting here, and we compare about this. Will be compared with the Bose constraint case. Okay, and then the last part here is like, well, for any possible observation of my uncertainty vector, so I have some recourse actions, like could be redispatch using some limits of the reserves. It could be the redirection of the flows. Basically, it's the OPF equation for any possible output of U, right? So it will be feasible for that. Well, this is kind of the function related with the with imbalance. It's a cost function. We are using something even more simple than this cost function. Okay, it's important to understand that whatever are the deficiencies on the first stage here, my power, which is dispatch, what are the generating unit that will be online, etc., is changing the operational condition of this recourse action that I have in the second stage. So if I have generating unit online, so this vector X actually will be representing this unit is online, and we have some reserve capacity for responding for any possible change. And also depends for any particular scenario that it can happen. And this is actually defined by this uncertainty set U. Okay. Okay. So if we want to go into detail, here even looks like very messy. This is kind of the very complex way of representing that. So we have this minimization problem, typical minimization, which accounts for shutdown and startup cost, some generating cost. This is energy cost, energy related cost, and some costs related with reserve booking capacity that we need to keep for the case of uncertainty in the second stage. This is how it looks like in very compact form in vectors of my objective function. Then I have, of course, I have some balance equations for every particular hour and every particular node. So we are considering here grid. Some constraint related with the capacity of the lines, and this is Kirchhoff and voltage law. S are the proper matrix, which is represented by these two set terms. I have some limits of the generation capacity of every generator that I have in my system. V's are representing the on-off or online, offline binary variables. So that's this maximum capacity and minimum capacity. So I have some limits of reserve that I can provide with each generator, which also depends if this generator is actually online or not. There is some ramping constraint, which accounts for not only intra-hour ramping constraint, but also can account for the starting up ramp constraint, which are also this A is a function of these two binary variables. You can find more details on some seminal paper of Jose Manuel Arroyo and Miguel Carrion on this unique commitment formulation. And once again, this cost, this is already a value, and these are represented by this feasibility set. This is another set of constraints which are representing minimum time of starting up, etc. So there are other. This is very full formulation of the unique commitment problem. Okay, the first part actually is a classical unique commitment problem with all the details that you want to give. And in the balance equation, you see here, like you have this U hat, which is representing the nominal production of the point forecast production of renewable energy generators. And P is just incident matrix that maps this vector to particular nodes. Okay, so the first part, as I mentioned before, this is classical unique commitment. It's deterministic in somehow because we just use this point forecast value. And then we have this second part, which are adding another two levels to this problem, which consider the uncertainty. So in the second part, we try to find what is the worst case scenario. So this will be kind of umbrella. And the cost function here is related. E is basically identity vector, so it's ones, and x plus and x minus are representing the slack variables or the imbalance. They are slack variables at the balance equation. So in the balance equation, in this case, we have added two additional variables, which are representing the positive imbalance and negative imbalance. And positive imbalance, one is related with the renewable curtailment, the other one is related with load shedding. And of course, so they are limited with the possibility. So what we have in this case, we have this is kind of OPF. Now, binary variables are fixed because are coming from the first stage. And ramps, reserve also are actually given are the fission of this unique commitment. So we have the fission of ramps up, ramps down, generated power, this binary variable representing on-off state of the generating units, the commitment. Okay. Well, I'm representing here some duals. So the first observation looks like very sophisticated, but this is just some of the classical formulation of the unit commitment problem. The first observation is this inner problem is an LP, it's a linear programming problem, which is function of the commitments and energy dispatch and booking capacity of these reserves. And also it is function of any possible output of my uncertainty vector. Okay, but this still is a linear programming problem. So whatever is, if I'm giving already some value of X and U, I can quickly compute what is the optimal value of this LP problem, which is representing the minimum imbalance. We will take advantage of these observations. Again, this is the compact form of the same problem, and this part is the LP problem, which is a function of X and U. Okay, so how we build, let's go back. So I will show you two ways of building this U, data-driven, and this box constrained uncertainty set. So how we can build this data-driven uncertainty set, so we can actually have some of historical observation, let's say for some k days, previous day. Okay. And for every day, I will have an observation, which is, let's assume that I have 24 hours and two renewable energy generator. I have only two wind farms, okay? So I will have a vector U for a particular K, which is the first 24 hours from 1 to, okay, let me write in a different, like this. For this will relate with the generator number 1, and this for renewable energy generator number 2, and this is from 124, and this is from 124 hour, right? So this is basically a vector of 48 dimensional vector. Okay, and then for every possible observation every day, I will have one of these vector. Here is here below, I have some again, I was using Cassie before, but this is now U. I changed by U. Here I have the uncertainty of dimension number 1 and dimension element number 1, let's say, and this element number 2. Okay, this is U1, this is U2. So how I can define, and so this is the projection in 2 dimension, but I have 48 dimensional vector and 48 dimensional space. How I can represent that, this uncertainty set, basically I can do a convex combination of all these particular points. And this convex combination is representing the convex hull of the observations. And just is a very simple way of doing convex combination. Is just choose some alpha, and with alpha between 0 and 1, and the summation of all the alphas equal to 1. Okay. Okay, this convex combination is kind of representing the overall set that we have inside here, and the interior points actually are counted to this convex combination. You know, like with the stream points, the one which are forming this convex hull will be enough, but for simplicity, we use all of them. We did some preliminary work on finding just what is the convex hull, what are the vertices, and just not consider the interior points. But we observed like this computation of this convex hull actually was adding additional time for the overall process that was not actually worth. So it's better to, in practice, was better to consider all the observations. okay, even if they are in the interior of this uncertainty set. Okay. So the nice thing here is that the only thing that we have to give as parameter for this uncertainty set, we are a market operator or regulator or system operator, is just the number of days or the number of historical data points that we want to consider. And this can actually be done somehow easy. So we have to decide what is this capital K. Okay, it can contain like the previous 30 days. It can contain like the previous 30 days plus what happened the last year around this period, something different. Okay, so how looks like the budget constraint uncertainty set? Okay, this was my data driven. How looks like? Well, typically you have, again, this is the vector. This is 48 dimensional case for my particular sample. It's a vector that given by this u, and which is around to some reference value. Okay, so this u hat is this nominal value, which sometimes is representing, yes, this, let's say this is u hat 1, here is u hat 2. Okay, and those are representing some nominal value, some point forecast. And then I have an additional delta, so delta plus, so the nominal value of wind generation of particular point node 2 can actually go up, some delta plus 2, and also can go down, some delta minus 2, right? And the same for the same one. This is what is written in here, okay? And Z basically is modulating how much amplitude we are taking from this delta. It can go from 0 up to 1. So it's 1 is the maximum amplitude and 0 is nothing. Okay. So far up to here, this is Soyster formulation. Okay. Well, the budget actually says like, well, I will give percentage of how many changes I can have, how many amplitudes I can have in total as a one, and this gamma is representing this budget. So I'm saying like the total variation of these, either positive or negative, have to be less equal to this budget of uncertainty, which is normalized with the number of renewable generation elements that we have. Okay, so if the budget is, let's say, 90%, say like, well, it could be 90% of the elements can actually change. If the budget is, let's say, 0.5, 50%, I can say like only half of them can change simultaneously to the maximum value. Okay, and this is what is representing here. For example, for a particular case of 2 dimensions, this is even simple. If I have a budget of 2, so the uncertainty set actually is represented like this box. Okay, but if I have a budget of 1, I have the uncertainty set represented by this other box, right? Only either U1 or U2 can actually go to the maximum, to the minimum. The other one must be in the nominal value. Okay, that is what is represented as gamma. Okay, you can see well, you already have a very good observation here. Like when we are adding this budget, some of the observation actually could lie outside of the uncertainty set. And we are solving robust optimization problems. And we believe like these robust optimization problems should be robust in terms of the possible outputs. But we see like, well, there could be many of those scenarios that we already observed cannot be actually feasible, or it can fulfill this limit of the imbalance limits. Well, we can add also, this one is added budget, and gamma represent the budget among all possible renewable unit that they have. Also, you can have a budget related with the number of hours. So how many hours can actually change. Okay, this is the classical budget constraint uncertainty set for this multidimensional space. And then let me show you how we solve this problem. Okay, remember this problem is a 3-level problems. And we are going to use a well-known method, which is called column and constraint generation. And the basic idea of this column and constraint generation is like to create a master problem, which is solving some reduced version of the original problem, and then some oracle or subproblem, which is given valuable information to this master problem. So we are adding at every iteration new set of constraint variables. That is why I call column and constraint generation. So the first observation that we can have here is like, this is my original program here on the left. Okay. We can say, well, let's start reducing or relaxing somehow this problem. Instead of maximizing for this uncertainty set, let's pick up some particular scenarios. Let's reduce the space of search. And let's, I call here UJ. Okay, with J from 1 to capital J. Okay, well, if I have that, so actually this part actually can be writing just like this, right? Sorry, this. Yeah. For every possible scenario that I have included already. Okay, this is, I think you can see that, right? So yes, I'm repeating for this particular set of scenarios UJ with J from 1 to capital J are explicitly put into this limit constraint. So for these particular scenarios, I'm fulfilling the maximum imbalance is below of epsilon. Okay, but of course, so these particular elements or scenarios are just part of the full uncertainty set. Those UJ are small searching space, while the U typically have infinite number of scenarios. Remember those areas in gray color that I was showing before. Okay, so what we can, well, because this is accounting only for, you already have seen that, this is accounting only for a reduced number of scenarios. This problem will be actually represented a lower bound of the original problem, because we account only for a particular number of scenarios. As we are adding more and more scenarios, the operational cost will be increased just to be able to respond to the any new scenario that is coming. Okay, well, how we still have this mean operator in the constraint. What I'm going to do is just transform this mean operator, which is a LP problem, into his dual. So this guy actually is the dual of this problem, right? And I can do this because this is a LP problem. This is nice because I can dualize and then replace this problem by its dual. But now it's nice because I have a max operator. Omega are the dual variables of this lowermost problem, the second state of the recurse problem. And capital omega is representing the set of dual constraints. So this is nice because the maximum of this problem have to be less equal to the epsilon. So I can just enumerate these capital J cases like this, right? So I can just enumerate, find what is the omega for this, some omega feasible for this capital J. And then for any possible values of omega, this have to be less equal to the epsilon, right? And now omega, these dual variables are part of the decision variable. So this is this problem is a MILP problem, but this is just single level. Okay, this will be my master problem. So what I'm going to do at every iteration, so I'm going to increase the size of these scenarios. You can see, like, if we account for the infinite number of scenarios, so I will have infinite dimensional problem for all possible scenarios within this uncertainty set. This will actually be equal to this problem. I cannot do that, so I will try to pick up what are the representative scenarios that is giving me a very good approach for this original problem, or even the exact values of the original problem. But this is nice because I have a lower bound of that. So what I can do, how I can add new scenarios to the master problem. I will use the two lowermost problems. So this is the problem that I have here. Okay, this is an uncertainty realization, and this is the second stage decision problem. Okay, this is the redispatch with the minimal imbalance. Okay, for this problem, I know, like, X is usually given, right? The first stage decision are given. So here X is given. So whatever is the value of X, let's assume that X is not optimal. I will have some value here, which is representing some imbalance. Somehow I'm able to derive some upper bound from here. And what are the typical things that it's done in the literature for dealing with this problem? So I dualize this inner problem. Again, this is an LP problem. So I do dualization. And then I have a max. I will have a max in U, a max in the dual variables. So this is a max, so that I can join these two problems. There are bilinear terms in this case from some dual variables from the inner problem and U variables. But there are reformulation to make this linear by adding linearization, so plus some binaries which are needed. So we can end up in a sad reformulation of this problem. This is an sad reformulation of these two lowermost problems, but this is a MILP problem. It's a Mills integral linear programming problem, which in principle is NP hard. Okay, but this is the thing that most of the paper are doing with some specific variation of that. So here we are proposing the nest. So I say, like, instead of solving this problem for reformulating, I will just fix U for every particular observation. And typically observations are few of them. So there are tens. Is the order of tens, right? Like 30 days or 40 previous days, right? So I can solve, like, for 40, 50, 100. I can solve 100 LPs, this inner problem. And this actually I call inspection based, but this is an enumeration of possible scenarios. Because this is an LP, so we know these have polynomial time for resolution with using ellipsoidal method. So we know, like, we will have polynomial time, but in addition, this can be easily parallelized, right? Of course, branch and bound methods for solving MILP problem can be also parallelized, but there are some processes that have to wait until solve different nodes. But this is kind of a natural way of doing parallel computing for every particular scenario. Okay. But here is a question. So, like, remember, I told you I want to consider not only the particular scenarios that I have observed, but I want to consider any possible scenario, which is this region, this uncertainty set. And this is two-dimensional, but just think about any high dimension order of this. So do we cover with just the enumeration of each particular scenario, do we cover the full spectrum of all possible scenarios? And is it still robust? Well, if we cover all of them, we'll be robust, okay? And the answer is yes, of course, and the observation is the next, okay? Let's look again to this problem. This problem is an LP, right? And this LP depends on X and U. And this problem actually is convex in U, because U is an independent term of this balance equation. So it can be actually proved very easy that let's say this is a function that J of U, this J is actually a convex function. What does that mean J is a convex function? So I'm maximizing now in U this JXU, a convex function. I know U is within some limits, right? So there is some bound. This is just, let's say one-dimensional. And then I have a convex function. Whatever is this convex function? Well, again, so we can recall these properties of convex optimization, and we know like a maximization of this convex function will be always, the solution of this maximization of this convex function will be always lying in one of the stream points of this set U, right? So nice. So I know right now, like any possible stream point of this data-driven uncertainty set could be a solution of these two-state these two lowermost problems. Okay. And then the solution will be depend also on X. So the idea is just to add at every iteration what is the best what is the worst case observation, right? So considering just the stream points will be enough for doing everything. But as I mentioned before, in practical way, it's easy to compute the LP problem for all of observation that I'm considering in my data-driven uncertainty set, instead of doing a previous step for finding what are the stream points of the convex hull. This is a practical observation, but we can do the thing. Yeah, the idea of this column and constraint generation is actually coming from this paper in 2013 from Chen and Xiao. And this is how it looks like the overall problem. So I have a master. From the master, I can have a optimal solution for this particular master, which is not optimal for the overall problem in principle. And I can derive lower bound. Then I run my oracle, and this oracle can be run in parallel. I get an upper bound and a new scenarios that will be included in the master problem. And then I can iterate until the upper bound and lower bound actually is within some limits. Okay, just keep in mind, like I will compare also this mill-based and inspection-based case in my case study. Okay, and this is kind of let's say, simulation of how it looks like the column and constraint generation. I think I will go fast. The problem itself with just the unit commitment, with considering all possible uncertainty realization, is something like this. But when I add in additional constraints, so each additional constraint actually, let's assume that adding new constraints to the overall problem. This is very conceptual view of what is doing the column and constraint generation. Let's assume that this is the optimal solution of the overall problem. All constraints are, of course, so many, so I'm going to add one by one at every iteration. So the idea is just to start with just nominal points. And I may have this x1 and x2, for example. This is the solution space, and this is the uncertainty space. Okay, so I'm solving that. And for this particular X at the iteration 1, I will check for all possible subproblem in the oracle. What is the worst case? Okay, and then I add this one to the app. So in this particular case, I found the solution in the space solution. In the first stage it was here in this corner in the minimum, and this was representing the, let's say, 1 point in the worst case is in here for this particular case, 0, 0. Okay, so then I add this additional constraint, right, which is representing this 0, 0, which in my solution space will be something like this. Okay, and I'm solving again, and this iteration have an additional set of constraints representing the optimal operation after the observation of this first scenario, this one. And then solving that, so I can find a new worst case scenario, which will be in here, okay? Because of course I have a new X start in the second iteration. Okay, so I can do this iteratively, and you can know, like, we don't need actually to include all the observations. It will be enough to have a few number of scenarios for having the optimal solution of the original problem. Okay, with that, so we are ready. Good. Okay, let me show you a case study, and then I give you room for questions. I think I'm standing quite a lot. I'm going to show you basically a force bus case study, and then just for scalability, what was the result on this standard, IEEE standard 119 bus test case. So what we did here is for a 4-bus system, is an illustrative case with 24 hours and 2 renewable energy generators. So the vector of uncertainty is 48. We run different type of models of frameworks. We run this, what we call DD, data-driven robust unit commitment, which is our approach. And we run several instances. K is representing the number of previous days that we are using for building this data-driven uncertainty set. Okay, we compare again this. This, I think we call it in different way here. This is budget constraint unit commitment. Okay, that depends on this gamma and lambda. These are the budget constraints. So this is the classical approach for this robust optimization framework. And also we compare with the baseline stochastic unit commitment, right? So this is a stochastic unit commitment. So we fit our historical data to some distribution, log normal distribution, and then we sample. I remember, if I remember well, it was 100 scenarios, and then we solve the classical two-stage stochastic unit commitment. We ran with real data from this global competition. We ran an auto-sample analysis for 336 days. Okay, so the idea is like for day number D, so we look backward for the previous K days, and then do the unit commitment for the day D. Okay, and then just accumulate this information to see how was the performance on the day D, right? Okay, so this will be D, and this is D plus 1. So the next run for the next day, so we do the same thing, and then we are moving this window of K in the future. So we always take the previous K days. Of course, it has to be fair. So with the both constraint unit commitment, we have run different instances with different budgets of uncertainty, which is kind of very complicated to decide what are the best one. But we have run different ones. Here there are some results. For instance, in here, what we have is the instance of distribution data-driven robust unit commitment using 42 previous days. Okay. For the auto sample, it means like 336 days. We summarize here the average time for every day. How much do we need for every day for computing that? For example, this is using the inspection base of this enumeration, 20 seconds in average for solving the problem. And this is using the MILP approach, right, for the Oracle. And this is inspection based. Okay, and then we have different instances. We see like, well, this is considering less days, so somehow we are less, the average cost is less than using more days than the previous day. We also compare with different instances, like 90 represent like 90% of the uncertainty of the nodes can actually change to the maximum. Okay, for example, this last case is 50%. And the last one, of course, in terms of computational time, so we see like this data-driven actually perform pretty well, even better than the cases of budget-constrained robust unit commitment. Of course, it's better than a scenario stochastic unit commitment. We also observe, we plot here some additional metrics like loss of flow probability and probability of wind spillage. And we see like here in this plot, average cost for this auto sample analysis and this loss of flow probability. Like in general, the data-driven robust optimization, is somehow dominating, right? It's somehow dominating the classical approach from vertices seams, and this is a stochastic. So I think like, well, this looks was very nice. I can give you why, for example, is dominating that. Why the data-driven dominates in terms of the average cost and in terms of the reliability. So these basically are representing reliability, these metrics. So if you see in the case of two renewable energy generators, two buses, is the case of this 4-bus system. And then I giving you like 50% of the nodes can actually vary. So it means like either one or two can actually go to the maximum to the minimum. So this is what is represented by here. This uncertainty set is this gray area. And you can see like many of these stream points, like you have high wind, and you have probably here low wind, and those are missing. So they are not considering this correlation, and actually we are missing this information, and this actually can have an impact. So this budget parameter actually is pretty complicated to see. We have here also an additional plots for this particular case and for a particular day, the day 43 of this rolling window. And we represented what were the scenarios that Columnar constraint generation were selecting to send to the master problem. Okay, and here there is one bus, and here is the other bus. And you can see, for instance, what is happening here is like in the orange are the, I think was 8 scenarios. In total were 8 scenarios. The orange are representing the scenarios that were actually found by the Oracle to be part of the master problem. The gray are not part of this master problem. And you can see here interesting things, like you have like very low wind cases, very high wind cases, scenarios. You don't have like 100%, it's up to whatever was the observation. So the wind is not producing in any of those particular days up to 100% of the capacity. if I remember, this is normalized or not. But there is an important observation here. The Oracle actually found scenarios with high ramps, like you have a sudden drop from the power produced by the wind farm, or sudden increase, right? The same for this particular bus. You have these very stressful scenarios that can actually affect the operation of the generating units. So it's somehow you need to capture this. This is also represented in somehow here. Here we are representing what are the variation between 2 consecutive hours. Okay, and then in orange, again, those are the scenarios that were part of the master programs. With those scenarios were enough to capture to get the same solution of the full problem, or so we are getting the SAT solution. Okay. And then when I feel I'm not going to stand, this is a scalability test for 119 bus, and I think like I will probably finish here, so we have room for questions. And then so we actually found pretty appealing this data-driven approach for dealing with these operational problems. We found also tractability and by using this column and constraint generation, which is very good. So we have very nice computational times and very nice performance in terms of comparing the data-driven robust unit commitment with the classical budget constraint, or this boss-like constraint uncertainty set. Of course, the way that we have built the data-driven uncertainty set can be actually extended, and even we use historical information, but you can also use forecast errors. Somehow we have some nominal points, and around of these nominal points, we may have some errors given by some probabilistic tools that is now pretty common in the industry, in the market operators or system operators. So we can build those uncertainty sets around this forecast error instead of these historical values, or maybe other type of information. So it can be actually extended in other kind of information that we may have for understanding the uncertainty. Okay, so if you want to have more information about what we are doing, so we are here at Skoltech in Moscow as a new university, and we have a group. It's called Power Market Analytics, Computer Science and Optimization, and we do a very we work in a very exciting program. So you may have a check of this website. Yes, I think I'm finished here. Thank you for your attention, and if you have questions, I'm happy to answer any questions.